How we doing, guys? Looking at trigonometric identities today. If you're in text and test 4, it's exercise 8.1, page 307 that we're working on. So trigonometric identities are relationships that exist between sine, cos, and tan, basically. Um, we're going to start off back with the unit circle that we've seen before. That's a circle that has a radius of length 1, and there's some argument or some angle made for with respect to the x-axis that we're always going to call theta in these questions. What we've seen before is that the x-coordinate then is the cosine of theta, and that the y-coordinate is the sine of theta. If you like, you can say, well, sine is opposite over hypotenuse, but hypotenuse is just 1, so sine needs to be the opposite. And similarly, you'll say cos is adjacent over, well, the hypotenuse is 1, so cos needs to be the adjacent. So cos is the x-coordinate, sine is the y-coordinate, and then coming to our usual triangle here, opposite, adjacent, hypotenuse, tan theta is always defined as opposite over adjacent, which for us now is sine theta divided by cos theta. So there's an identity. That's a relationship between tan, sine, and cosine that we're going to be using now in our work that we're looking at now. Another one, well, if you apply Pythagoras here, you'll get cos squared plus sine squared together gives 1 squared, which is just 1. So you get sine squared plus cos squared equals 1. There's an important identity. That one gets rejigged quite a lot. So one example would be sine squared theta is 1 minus cos squared theta, or cos squared theta is 1 minus sine squared theta. I'd encourage you to try some of these. So on this one, maybe try tan of 30 is the same as sine 30 over cos of 30 in your calculator, or pick 27 or something strange like that. Here, try sine squared of 50 on your calculator. This is just a rejig, but if you want to try this one, sine squared of 27 equals 1 minus cos squared of 27, you can try that as well. Taking that identity that sine squared theta plus cos squared theta is 1, if we divide through by cos squared theta, sorry about that, cos squared theta, sorry, don't put that plus there, 1 over cos squared theta. We get sine squared over cos squared. Well, that's sine over cos is tan, so this is actually tan squared plus 1 equals, now that is called sec squared. Let me just tell you where sec comes from. 3 identities we haven't talked about: 1 over cos theta, 1 over sine theta, and 1 over tan theta. Well, 1 over tan is called sec. 1 over cos cotan squared, and 1 over sine is called cosec squared. These ones you don't really see. Not squared. Excuse me. You don't really see these used all that much on the leaving cert, but they are there in your log tables. In fact, all of the identities were looked at, and they're listed under the trigonometric identities, trigonometry, page 13. On page 14, you'll see a lot of these identities that we're going to work with in this whole chapter. Excuse me, page 13 as well. So the ones we're looking at right now, we're up here on page 13. Cos squared plus sine squared gives 1. Sec squared is 1 plus tan squared. We just saw that one. Those 3, sec A is 1 over cos, cotan is 1 over... it's 1 over tan, but that means instead of being sine over cos, it's cos over sine. Cosec is 1 over sine, and then tan is sine A over cos A. So all these for this exercise are there on page 13. Looking at some questions, on page 307, question 1 that they've asked about there says, show that cos A tan A will give sine A. Okay, so you're trying to show that this will equal sine A. Well, if we take our identity for tan A that we now know, we could say, well, you can always replace tan A with sine A over cos A. Okay, and remember that sine A, cos A, these are numbers just like any others, so you're multiplying top and bottom of a fraction. That's if you like, a common factor top and bottom on the fraction by cos A. So cancelling that out, you're left with sine A, which is what they've asked us for. Question 9 uses a different identity, that 1 minus cos squared, you see it here. Okay, well, we can replace that. That's the same as the square root of 1 minus cos squared is the same as the square root of sine squared theta. Okay, now what we're trying to show, in question 9, is that this thing ultimately will give cos theta. So where do we go from here? Well, the square root of sine squared is just sine theta. And just to do two steps at the one time, tan, remember, is sine A or sine theta over cos theta. Okay, so you've got that common factor of sine theta again, top and bottom, you're left with 1 over, if you like, 1 over cos theta. Multiplying top and bottom by cos theta, you get cos theta on the top, you get 1 on the bottom, which is what they've asked you for, cos theta. Question 15 gives it something a little bit trickier. It gives 1 over 1 minus sine A plus 1 over 1 plus sine A, and they ask you to show that that gives twice sec squared A. So sec is 1 over cos squared, so twice 1 over cos squared. Now, what you need to recognize here, and it's a bit tricky, is that this 1 minus sine squared is a difference of two squares, and in fact those are the two factors. So you can get rid of that quite easily by saying that's multiplied by 1 plus sine A, and I'm going to get 1 minus sine squared A when I multiply that out. Over here, multiply top and bottom by 1 minus sine A, and again that difference of two squares is going to give me a denominator of 1 squared plus, minus sine squared A. So what do I get here? On the top, 1 plus sine A divided by 1 squared minus sine squared A plus, over here, 1 minus sine A divided by 1 squared minus sine squared A. You might have actually not even gone as far as saying it's a difference of two squares. You might have just been trying to get a common denominator here and multiply top and bottom here by this denominator and top and bottom here by this denominator. Either way, you get 1 plus sine A plus 1 minus sine A, and because you've got the same denominator, they can disappear. So you get 2 on the top and 0 where those sine A's are. On the bottom you get 1 minus sine squared A, but of course 1 minus sine squared A is cos squared A. Okay, that's our rejigged version of sine squared plus cos squared equals 1. So that's almost what we want. 2 over cos squared A. Well, 1 over cos is sec, so that's 2 over, how do I say this? 2 times 1 over cos A squared. And that is twice sec squared A. Another type of question you'll be asked with these is questions that involve the sine rule and the cosine rule. If you remember, the sine rule said for a triangle where sides are called A, B and C, and then the angles opposite those sides respectively are capital A, capital B and capital C opposite lowercase c. The sine rule said A over sine A equals B over sine B, which equals C over sine C, and you pick whichever one of those is most useful for you to use. Another rejigged version that can be useful, sine A over A is sine B over B, so you're just inverting all the fractions, sine C over C. So just picking, say, these two, quite often in these questions it's useful to say, well, sine A then, multiplying through by A, gives A sine uppercase B over lowercase b. That's a version of the sine rule, okay? Both of these are other versions of it, and you'll have to rejig it. Really, this exercise is more algebra than it is trigonometry. You'll have to rejig these as you go. Cosine rule says, and I'll just give one example, a squared equals the other two sides squared, b squared plus c squared minus twice their product times the cosine of the angle in between them, which in this case is a. Okay. Equivalently, you could have b squared equals c squared plus a squared minus twice ac cos b, or you could have c squared equals a squared plus b squared minus twice ab cos c. Okay, so there's a few ways you can present the cosine rule. I've only got it this one way. In this exercise, they tend to get cos a by itself is the most useful way to work with it. So moving everything over to the left hand side, you get a squared minus b squared minus c squared is negative 2bc cos a, dividing through a squared minus b squared minus c squared over negative 2bc is cos a, multiplying top and bottom of that left hand side by minus 1, you're going to get b squared plus c squared minus a squared over 2bc. Okay, so that's one version of the cosine rule. The log tables gives you the original version. Where does the cosine rule crop up? On page 16 it gives you this version, so you need to be able to rejig it yourself if you want to rejig it, and you can see the sine rule there as well. So I'll finish with question 19. Oh sorry, just to rejig that could also potentially be cos b. Okay, so now b is where a is, so that's your b. So you get a minus b squared, and that's the only one that's different. So that's going to be a squared plus c squared over twice ac. Okay, or potentially cos c. So c goes in this last place now. You get a squared plus b squared minus c squared over twice ab. Okay, so depending on the question, you might want to use cos a, cos b, or cos c. All of these questions assume you're working with this general triangle. That's the notation. So here in question 19, we're going to replace cos c. So that says b times, we're going to replace cos c with this a squared plus b squared minus c squared over twice ab plus c times, and we're going to replace cos b with a squared plus c squared minus b squared over twice ac. Okay, and what we're trying to show in question 19 is that this will all give a. Ultimately, when you work this all out, you're going to find yourself back with an a. Okay, we'll start with, you've got a common factor of b, top and bottom. So by taking that out, you now have 2a as your denominator, which means you're now allowed to add these fractions together. So what do we get? Well, you get yourself a squared plus b squared minus c squared plus a squared plus c squared minus b squared all over twice a. B squared take away b squared, 0. C squared take away c squared, 0. So you're left with 2a squared over 2a. 2's cancel, a's cancel, and you're left with just a. Okay, so that tidied up. And sorry, I said I'd have a look at question 25 as well, and I'll finish then. 25, use the sine rule to prove that sine a minus sine b over sine b will give us ultimately a minus b over b. Okay, a minus b over b is what we're going to work towards here. So sine a, using this version here, you can say, well, that's going to be a sine a over b. Take away, leave the sine b, a sine b, excuse me. Take away sine b over sine b. And I haven't changed sine b because I can see now I've got a common sine b all the way through this. So, what's the easiest thing to present that? I'll take sine b as a factor on the top, and I get a over b minus 1. And on the bottom, if I take sine b as a factor, I just get 1. So when that cancels, you're left with a over b minus 1. which isn't quite what they've asked for. But if you want to put that together as one fraction, you'll say, well, 1 can be written as just b over b. So what do you get there? A minus b over b. Okay, I'll leave it there.